Hi, my name is Rafael Landa. I'm a senior data scientist at Tokyo in HCC. My co-author is Dr. Eduardo Gilding from the Department of Petroleum Engineering at Texas A&M University. He was my undergrad, master's, and PhD advisor. And the title of our paper is the windowing algorithm, dimensionality reduction in gray box systems identification of reservoir network models. To start, let's talk about the problem we have. Think of a petroleum reservoir. This is a porous rock in the subsurface, where the porous spaces are filled with fluids, such as oil, gas, and water. We want to produce these fluids, so we drill producer wells and start production. With time, reservoir pressure and production flow rate decline. To mitigate this issue, we start to drill injection wells, which enable us to maintain and/or increase reservoir pressures and production rates by injecting fluids such as water and/or CO2. It's really important for us to have simple yet reliable models to forecast reservoir performance and infer subsurface properties with minimum data requirements. Capacitance resistance models can be used for this purpose. They consist of networks of material balance equations and have been previously applied to water flooding, CO2 geological sequestration, and geothermal reservoirs. The name is due to analogous behaviors of reservoirs and capacitor-resistor circuits. Both systems store energy. In the circuits, electrons are stored in the capacitors, while in the reservoir, fluids are compressed and stored in the porous media. Flow and resistance to flow can also be described in both systems. The governing equations of both systems are also similar. As you can see here in this figure, there are multiple types of representations for capacitance resistance models. For example, the simplest one is the single tank representation, where the reservoir is described through a single material balance equation, and we have a single pseudo injector that sums up all of the injection rates and a single pseudo producer that sums up all of the production rates. On the other hand, the injector-producer based representation, CRMIT, is represented through a network of material balance equations where we have one material balance equation per each injector-producer pair. It turns out that all those CRM representations are linear dynamic systems. Therefore, state space equations provide a generalized framework to represent the dynamics of these systems in the time domain. The inputs are injection rates and producer's bottom hole pressures, while the outputs are liquid production rates. For a given CRM representation, the structure of the matrices A, B, C, and D are known. However, the values of parameters need to be learned by feeding time series data of inputs and outputs, which characterize a gray box systems identification problem. Now let's consider this case where we have 13 producers and 12 injectors, and all of the producers are connected to all of the injectors. So we have in total 156 connections. The problem here, though, is that we are connecting injectors and producer pairs that are very distant. Like, for example, we could be connecting this producer here with this or this injector, which are very distant, and usually we don't expect to see this type of interference either from like the pressure support or the streamlines. So what this tends to give us is like we are including spurious correlation from the production data. So in order to avoid this, we could essentially apply the dimensionality reduction technique called the windowing technique, which is what we are going to show here which is essentially you select the wells that are within a certain window or that follow a certain criteria. So here we are, for example, just using the Euclidean distance in a way that we essentially just select the adjacent injectors to a given producer. Okay, so instead of having 156 connections, we have only 40 connections. So this results in a much reduced number of parameters to be estimated through the gray box systems identification algorithm, and is a type of regularization for our models. As shown here, the gray box systems identification consists of a nonlinear least squares problem with inequality, equality, and box constraints. While this represents the problem for a fully connected network, the windowing algorithm reduces the dimension by generating a reduced form for the matrices and vectors shown here. Such reduced form is obtained through a simple matrix multiplication. The contribution of this paper is to provide the algorithmic way for the windowing technique, including the derivation of the transformation matrix, TI, for different representations. The size of the window that we will select depends on the reservoir properties. For example, if it's a naturally fractured reservoir or a reservoir with high permeability strips, we may prefer to use bigger windows. On the other hand, also, it's important to consider the type of phenomena that we want the model to describe. For example, to depict the advance in the waterfronts, which is usually described by streamline, as shown here, the streamline allocation factors, usually those are restricted to only adjacent injectors of a given producer. On the other hand, the pressure interference, which is usually described by the material balance equations on CRMs, they can connect more distant injector-producer pairs. And we can see this here. This is a homogeneous reservoir where there is a flow barrier, which is depicted by the blue lines here. And we can see that the connectivities and streamline allocation factors for these three central injector wells are pretty much similar. However, for injector 1 and injector 5, we have this difference here, and it's essentially the type of phenomenon. Here, the streamline allocation factors are saying that between injector 1 and producer 4, we don't have any fluid going directly there. However, CRM confirms that although there is no fluid going directly there, there is an interference in the total production there. So because of the pressures of the fluid being injected here, it contributes to an increase in the production of producer 4. So in addition to that, we can also talk more now, a more complex example, which is for this channelized reservoir, where here we are showing the streamline allocation factors and how the streamlines are changing over time as we are changing the injection rate in this field. Okay, so again, we have that comparison between CRM interwell connectivities and streamline allocation factors, and we can see that through the CRM, an average of for all of the injectors, 22% of the pressure support was provided to producers that were beyond the 1,500 feet spatial window, so beyond the adjacent producers for a given injector. While for the streamlines, at most 1% of the fluid from a certain injector is allocated to producers beyond such window. So there is a big difference there. In this slide, we are showing the CPU time versus the number of parameters. So the windowing technique will reduce the number of parameters. And we are showing here results for essentially 20 simulation runs, varying things like the size of the windows that we used with the windowing algorithm, and also variations of cases with buttonhole pressures and without variations in the buttonhole pressures, and also different types of CRM representations. So what we can see here is that even like for these two relatively small reservoirs that we showed, we could obtain a reduction in the computational time of up to 90% in some cases, 80 to 90%. And that was essentially a very significant reduction in computational time during the systems identification phase. And as we go through bigger reservoirs with hundreds or even thousands of injectors and producers, we expect the benefits to be even more relevant. And finally, the conclusions. Capacitance resistance models can be applied to water and CO2 flooding, CO2 geological sequestration, and geothermal reservoirs. The windowing algorithm enables to drastically reduce the number of parameters estimated and computational time for systems identification, eliminates spurious correlation in production data of distant injector-producer pairs, adjusts to different criteria of selection of injector-producer pairs, and includes geospatial information in the model. In this paper, a simple and generic algorithm formulation for the windowing technique was introduced. Regarding the case studies, they showed that for even small reservoirs, CPU time could be reduced up to 90% depending on number of wells and model complexity. I would like to thank you all for your attention. Also, recognize the institutions that either provided resources for this research or allowed us to be presenting here. And I'm available for any questions you may have. Thank you so much.